some more about link distances. 3 GHz is beginning of super high frequency band. In this super high frequency band, we need free line of sight for communications. And this free line of sight means around 60 kilometers link distance. For frequencies from 3 to 10, 12, 13 gigahertz, it is possible to make a link with distance 60 kilometers, around 60 kilometers. From 15 to 18, 20 gigahertz, the link distance is around 30, 40 kilometers. And then for higher frequencies, around, for example, 35, 40 gigahertz, the link distance is around 4 or 5 kilometers max. And for higher frequencies, for example, around 90 gigahertz, the link distance is around 1 to 2 is very difficult to achieve. 1.5 kilometers. Because of these frequencies, over 50 gigahertz, atmospheric gases also play a very important role in attenuation. For calculation of these links, you decide what interruption time you will allow to your link. For example, you need 99.999% of time with stable connection.
Reliability.
Yes, reliability. And in this case, you take rain rate for 0.001%. This is around 50 millimeter per hour for Bulgaria. And we calculate your link with this rain rate. If you need 6 nines or 99.9999%, you will take 100 millimeter per hour. This is a reliability for telecommunication operators. And in this case, I think around 3 seconds per year, you will have interruption of a radio link. So that is the way you will calculate link budget, because you could take 200 millimeter per hour, but you don't have guarantee that it not will be 250 for a moment, and that is not a good idea to take higher rain rate, because your radio link will be very expensive, and you will use this over calculation, if I see like this, only for 1 or 2 seconds per year. and the cost is not equal to the time you use it. For example, I remember that the heavy rain occurred somewhere in Hawaii, I think in the 70s of the 20th century, and it is 2000, around 2000 millimeter per hour. 100 millimeter per hour is heavy rain, and this is 20 times heavier than heavy rain. But there are two very important tomorrow.
Wouldn't it be cheaper if you would use a different frequency only during rain?
It's not equal, because if you use smaller frequencies, the data rate will be smaller, and it is not equal. That's the problem. And here we have very wide, with high frequency we have wide spectrum, and we could transmit more and more data, and that is the situation. When I was a student, my teacher on this subject said that these frequencies above 15 gigahertz are almost not used, and this is very far away in the future when it will be used. But now it is more and more and more, and for communication I used for example 90 gigahertz from maybe 15 years for some applications. So the things are the same. Was with digital TV. When I was student, digital TV was only in books, and problem was the computer speed, frequency. Then in that time, computers was with frequency clock about 50 megahertz, 40, 60 gigahertz, and that was very small frequency for digital TV. And maybe 5 years later, everything changed, because the frequency clock of computers rise maybe up to 1 gigahertz now, for more and more. Took your 4, and the situation now is very different, and digital TVs everywhere, and there are no analog. So there are two very important things. Error is rain rate, and this is probability of such a rain rate, and that is the dependence probability on rain rate. If we have light rain,
High probability.
we have high probability. If we have heavy rain, we have low probability. That is the statistic. There's one other dependence that is almost the same, and this is area of array on array array. If you have heavy rain, the area is small. And if you have light rain, it could rain almost in the whole country. So that is very important. That is also taken into consideration when we calculate radio links. This effective path in the rain depends on rain rate. If you have heavy rain and, for example, you have 60 kilometers link distance, it could rain maybe on 6 kilometers of this rain when the rain is heavy. But if the rain is light, it could rain maybe on 40 kilometers or 50 kilometers from this 60 kilometers link distance. So there are models. I think this is ITU recommendation for rain attenuation calculation for radio links. 8383 of ITUR. ITU is International Telecommunication Union, radio section of this union, and in this recommendation are described models that you can use to calculation of rain attenuation. Atmospheric gaseous attenuation. It is caused by molecular resonance of oxygen and water vapors in a radio frequency band. In optical frequencies, also carbon dioxide and methane and some other gases affect attenuate waves. So in our case, for radio waves, oxygen and water vapor, you will see on the graph next slide that it has a resonance character. You could see the thin lines where we have a big absorption, high absorption, and between them we have some white part of white number of frequencies with small attenuation. But to see some other things, for frequencies lower than 15-19 gigahertz, you could not take into consideration this absorption. It is practically very small, and in calculation we don't take it, doesn't take it into consideration. It is significant for frequencies higher than 50 gigahertz. This is max, that is 60 gigahertz in the oxygen. This is second max. First max is around 22 gigahertz, and it is of water vapor attenuation. This is oxygen. Here is one small, around 130 gigahertz in oxygen too, and this one is 184, I think, in water vapor. Here, attenuation is around 16 decibel per kilometer. 16 decibel per kilometer is 40 times per 1 kilometer decrease of power. If you have 2 kilometers, that means 1,600 times decrease of the power. Very high attenuation in the atmospheric gases. Here, for frequencies higher than maybe 500 gigahertz, it is almost impossible to make connection in Earth atmosphere. You could use these frequencies only in the space where there is no atmosphere, in wave gases that is filled with
Nitrogen.
Azot,
No, nitrogen.
nitrogen. Okay.
What about this very pretty minimum?
This one.
Yes.
This is
Infrared.
infrared, and this is very pretty minimum invisible spectrum, and that is one of the that is why maybe we see in this spectrum, because there is no attenuation, and other is because the size of the eyes are similar to this wavelength, because if we view in this radio waves, our eyes maybe will be like this room or something like this. And other way is because with high frequency we have better resolution.
Mm-hmm.
In small frequencies, we need very big antennas to achieve good resolution. For example, if our eye active area is, for example, 1 square millimeter, this is, if we compare this with wavelength of visible light, it is very high, a very big antenna. For antennas with where the wavelength is 10 centimeters, we maybe will need antenna with radius about 10 meters to achieve the same resolution, or maybe not 10 meters. I think maybe 100 meters to achieve the same resolution, and that is one of also radars are the same problems. You are not able to make a laser, for example, in a low frequency, because in low frequencies you have antennas with very low directionals, very low directivity. So the light of main lobe of this antenna the width of this is big, and you will see in some angle, for example, of 60 degrees. That is not enough resolution for radio location to locate some object. You will set that in this direction somewhere there is an object. But for example, in 10 gigahertz, this angle will be 1 degrees. And this is different and more accurate. In optical band, if you have a lidar, not radar, but lidar, this I have a problem with words now. The same word I used. This resolution is very accurate. No, more accurate.
The other day I bought a cleaning robot with a LiDAR who was scanning my living room, so he can then not, go to the walls when cleaning. So I was watching it scan with the LiDAR, and it's most probably using infrared, is it? The robot that is scanning the room.
Yes.
It said it's a LiDAR.
Yes. If it uses optical waves, it is LiDAR. Also, some cars use such LiDARs for autonomic driving.
So what's the problem with infrared? Why are we not using infrared for telecommunication?
Because of for some frequencies we have high attenuation, and other thing is fog. Fog is very big problem. It is impossible to make infrared link if we have heavy fog. If visibility in the fog is, for example, 100 meters, link distance could be around 100 meters. You see in 100 meters if visibility is 100, and infrared link, for example, 200 is possible maybe, but no more. And that is the problem.
Is it only fog? Is it not also because there's a lot of other infrared sources around? It's not the atmosphere, but let's say something's heating.
There is no. This is not such a problem with other sources because this ambient light is not so serious problem. The problems are fog, the first problem and main problem, and other problems are vibration of antennas. Because you use laser sources and they have very small angle of radiation, maybe 1 milliradian. It is very small angle, and the radius of a laser beam in the receiver's plane is around, if the distance, for example, is 5 kilometers, it will be 5 meters. The diameter will be 5 meters. And if you have vibrations, for example, if you have a wind and antenna vibrates, sometime maybe the whole laser beam will be outside the receiver's antenna. And this is very serious problem. My dissertation was in this subject, free space optical communication. And other one is turbulence. It also causes a change of direction, but these changes are not so big. the main problem are fog, and therefore you could use radio link at frequencies about 60-90 gigahertz, where the data speed is not the same, but good enough. And it is not affected by fog, and that I said in the morning lecture. Rain affects radio link, but heavy rain and thick fog are not possible to occur at the same time. So one or other, and one line will work. When works a radio line, the speed will be smaller, but we will have connection. These free space optical links are very useful when we need some incidence links and links where it is difficult to make other decision, because to install one radio link, the size of antennas, the size of devices are bigger than in optical band, and therefore it is easier to install optical link, and also it is cheaper, because in optical band is used for wireless communication, are used the devices that is used in fiber optics, and their price is smaller than for devices that is used in radio frequency bands, where the data range is not the same, but different with one order from this that you can achieve in the optical band, for example. Because 60 or 90 gigahertz is the devices are very expensive now. Maybe after some years it will
Which
change.
band does the Starlink use, do you know? Which band does the Starlink use? The Elon Musk satellite internet. Starlink?
Most of them used around 12 or around 18 gigahertz. Maybe 18 used. I don't know the exact range, but that is the most useful ranges. Now they started to use and higher frequencies around 40 gigahertz for satellite communication, because the path in the Earth atmosphere is not so big. If you have that, it's good, because I could say something about if you have, if this is Earth surface, and you, for example, this is satellite. This is, for example, max height of 2 kilometers when a rain could occur. For higher altitude, on higher altitude there is no rain. Rain is on, and this path, if this angle, for example, is 30 degrees, if this is 3 kilometers, this will be 6 kilometers. so it is not so big distance. There is one important thing. This angle, elevation angle, is good to be over 5 degrees. Because for small angles, this part is very long, and in one hand you will have big attenuation in the atmosphere, rain and gaseous atmosphere, and also tropospheric refraction will affect propagation direction, because if here propagation direction changes very small, in satellite, which is at 36,000 kilometers, it will be very big deviation of the direction. So the angle is better to be over 5 degrees to the horizon. Over
I want
horizon.
to ask about fog. So what exactly do we mean by, like, we have fog here on low heights, so to speak, but higher in the atmosphere we also have fog that can be a problem for sending signals, for example.
Fog for optical waves.
Yeah.
Fog is with height to about 200 meters. There is no fog with bigger height than 200 meters. If it is on bigger height, the low part of the fog will elevate, and it will be maybe cloud but not fog. So the thickness is like this, about 200 meters. There is some clouds with high thickness, maybe to 1,000 meters. Maybe there are around 15 type of clouds and more, but it is meteorological classification of clouds. The max height of clouds is around 18 kilometers. And there are different, some of them you see that are more thick. There are different, but rain clouds are with height around 2-3 kilometers, and its thickness is not so big. In some clouds and this height, there are not only water in liquid form, but also ice crystals.
Ice crystals, yeah.
Yes, because of the height and the temperature. For example, if here temperature is 15 degrees, at 3 kilometers the temperature will be around 0. And in this case, in the clouds you have liquid and ice also, and then situation is very different. But for optical frequencies, it is easy to imagine the situation, because we see in optical band, and situation for optical communication is almost the same as we see. But for radio communication, the situation is different, because we don't see in this band and we don't know what happens in this easier way. So clouds and fog don't affect radio waves seriously, only optical waves. For radio waves, rain, snow and hail, and atmospheric gases. For optical waves, fog and clouds. Because for optical communication we use these frequencies where attenuation in the gases is small, because here is impossible to make a link, communication link, and only this one is the problem. Fog, clouds, and some dust that are in the air also, but it is not so serious. And this is the parameter visibility. Almost the same link distance as the visibility. If you could see at 100 meters, around 100 meters will be link distance in optical band. Okay, we have to take a coffee.